Hello everyone, I'm Emily and I'm a third year PhD student in the Modelling, Evidence and Policy group here at Newcastle. I'm using long-term datasets to analyse how climate change has affected the phenology of moths and how this may be affecting their interactions with their food plants. So today I'm going to talk to you about using mind maps to plan analyses of moth phenology. So what is phenology? You might remember this slide from a presentation I gave for NHSN a couple of years ago on my undergraduate research. Phenology is simply the timing of recurring natural events. So some examples here are bud burst, leafing out, egg laying and migration. And these are all events that happen at around the same time every year, which make them really easy to measure, but these are shifting due to climate change. So this is what I'm going to talk to you about today, and it seems quite overwhelming at the moment, but hopefully you will eventually understand what it means. So I've spent the last few years collecting data, developing the models and working on the theory I'll be using as the base of these models. And this mind map is a way I have represented some of the interactions I'll be using in the models. And I'll be going through what this all means later on, but first I want to quickly recap the results I got from my undergraduate work and how this leads to what I focused on for my PhD. So a quick summary of my undergraduate work. I found that a large-scale driver was influencing the emergent state of moths, and for 7 of the 11 moths I looked at, North Atlantic oscillation, which is an indicator of how warm and wet it is, was significant, and 6 of these moths formed cocoons in the soil. As well as this, moths were responsive to the nitrogen content of plants. This indicates that life history traits appear to be important in determining how species alter their phenology in response to climate change. So this has become a central part of my PhD research. So my PhD has been focusing on using life history traits to decipher what is driving phenological changes and how we might be able to predict them. Primarily, I'm interested in how restrictions of the life history strategy, so processes that impact the way a moth would go about its life cycle, can influence the phenological shifts that moth might experience. So, an example of a restriction might be a change in the North Atlantic oscillation that I included in my undergraduate research. So, in my undergraduate research, this appeared to impact species that form their cocoons in the soil more than others. Thus, species that form their cocoons in the soil were more restricted by this trait when the North Atlantic oscillation changed, and this influenced their phenology in turn. So, restrictions in the life history strategy can affect the direction, which is either an advancement or delay in phenology, and the magnitude, so whether this change is by days or weeks, of the phenological change that insect will experience. As a result, it also impacts the conservation status. Species that only have one food source are more likely to be affected by climate change because their food source is, they're more reliant on a single food source. In this example, the blue arrows here indicate that an increase in one thing, so an increase in the restrictions of the life history strategy, cause an increase in the direction of phenological change. Later on, you'll see some orange arrows. These indicate that an increase in one thing caused a decrease in the other, and black arrows, which are neutral. So other interactions that affect species are whether they are generalists, so can they survive on a range of food sources, can they immigrate, so can they move or track their ideal climate, their phylogeny, and whether they are multivoltine. So multivoltinism is how many generations in a year they have. Univoltine species have one generation, and multivoltine species have several. The ability to have multiple generations in a year may mean these species are more plastic and able to escape some of the negative effects of climate change. There has also been some studies that have found a move towards multivoltinism as growing season gets longer. So how do these relate to one another? So generalist species, as species become more generalist, they have fewer restrictions on their life history strategy, which in turn would reduce the magnitude of phenological change. And more generalist species will also have a better ability to immigrate as they will not be as restricted by specialist habitats. So it means that species who are generalist are less likely to have a higher conservation status than species who are more restricted by their food sources, so rely on, say, 1 or 2 species of plants. As the restrictions of the life history strategy increase, it means that the ability to immigrate decreases, because the fewer restrictions you have, the more likely it is you'll be able to move around and be able to survive in habitats slightly different to the ones that you're adapted to. So it means species that have fewer restrictions are much more likely to be able to migrate northwards and track their ideal climate. And phylogeny will probably have an impact on generalist species. So species that are more related are more likely to have similar food plants. So this means that species that are more related are probably more likely to be of a similar level of generalist species, so more or less generalist. The magnitude of phenological change will impact multivoltinism. So the amount that the phenology changes, so this is by days or by weeks, will impact whether multivoltinism is possible. So if a species phenology changes by just a few days, maybe this won't impact it, but by a few weeks, this can really decide whether the species has time in the year for more than one generation. And in the same way, the direction of phenological change is also really important, because if the phenology is delayed, then again, this might not mean much if it's only by a few days, but this could impact whether the species is able to produce those generations in a year. Whereas a species that is normally univoltine, if that moves by 2 weeks, and that's an advancement, so it has 2 more weeks in that year, it is possible that species might be able to move towards having multiple generations a year, and there have been some studies that have shown that this might be possible. So the habitat of species will also impact the restrictions of the life history strategy, and this includes whether it's urbanised or it's a specialised habitat, whether the host plant is available, the soil nutrition, whether the host plant phenology has changed, and the season length as well. Now, as supporters of NHSN, we know all too well how urban area can encroach on specialised habitats. So we can see here that urban area will, as it increases, it will cause a decrease in specialised habitat. Specialised habitat is also really important for whether the species is able to immigrate. So the more reliant the species is on a specialised habitat, so for example, a very specific type of woodland, the less likely that species is going to be able to move and track the climate that they survive best in. In the same way, host plant availability is really important. So this is related to, but not the same as, changing host plant phenology. So host plant availability is whether the plant is physically there. And this will be really important for species who start to migrate, because whether the host plant is available will decide on how restricted their life history strategy is going to be. And of course, soil nutrition impacts this. And we know that soil type changes throughout the UK. It's not the same. It's not a uniform type of soil. So obviously, as species start to move, they're less likely to get the plants that they're used to, because that plant might not be able to grow in the soil type that they're in the area they're moving towards. In the same way, host plant phenology is really important, because the availability of plants at the right time can be really crucial. So some species of moth rely on the young leaves on trees. So for example, oak trees, it has been found that oak trees are leafing out earlier now, and this can be a really impactful on species that rely on those early leaves, because they might not have changed their phenology at the same rate that the oak tree is. So it might mean that the oak tree is leafing out a few days earlier, but the moth species that rely on those leaves haven't moved their phenology at the same rate. So when the caterpillars hatch and they go to eat the leaves are now too tough for them to digest. Season length also really important, because the amount of time that a species has to gather the resources and move, so immigrate, and also the time they have to form as many generations as they need can really impact the survivability of the species. So abiotic variables. So we have rainfall, humidity, longitude, geology, latitude, temperature, and altitude. So many of these are related, as most climate variables are. And an increase in rainfall and humidity will likely cause an increase in the restrictions on the life history strategy. Whereas an increase in longitude will cause a decrease in rainfall, because as longitude increases, that means it goes more easterly, away from the sort of more western edge of the UK. Geology will impact soil nutrition. So as we know, we have different types of rock underneath the UK, and this really can impact the soil, which in turn impacts the host plant. Latitude, so the more northerly we go, the colder it is. And temperature, really important. So the higher the temperature, the lower the humidity, but the higher the rainfall. Urban area is really important for temperature, because man-made structures like concrete don't absorb light and heat in the same way as more natural structures like this, so a forest canopy, for example. So as a result, we get what is called the heat island effect. So this is where urban areas are much warmer than the natural area surrounding them, and this can be by a few degrees. Temperature will also directly impact the moth species. So insects don't respond to temperature in the same way as mammals do. Mammals, we produce our own heat. Insects can do this in some way, but nowhere near as much. So they are much more influenced by external temperatures than mammals are. This isn't to say that mammals aren't going to be phenologically impacted by climate change. There have already been studies on deer showing that their phenology has changed as a result of climate change, or being impacted by it. So it can affect mammals as well, but much more likely to affect organisms that are more responsive to temperature. And temperature will obviously also impact plants as well. And altitude, the higher you are, the colder it is. So there's a lot of variables here, and some of these are difficult to get data for, or it just doesn't exist. It's all well and good having the theory, but sometimes we're not able to look at the whole thing due to data scarcity. So I thought it'd be really good to show you what I'm actually able to look at in the model, because I think it's good to sort of see, you know, we have all the ecological theory and what we think might be impacting what it is we're looking at, but in reality, actually, there's only so much we can look at, and I think it's good to realise that. So the green boxes here show what I would like to come out of the model. So I'm really interested in finding out whether the direction and magnitude and multivolcanism of species has changed as a result of climate change. And the red boxes are what I'm going to be working out based on the other variables I have. So I have a really fantastic moth traits database that shows all of the traits, the life history traits that they have. So like when they form their cocoons, when they pupate, what plant species they eat, and all of these I'm going to be using in the models. But specifically, I can work out which species are generalist based on how many food plants they have, whether they rely on a specialised habitat, and I'll be using the spatial analysis that I'll be doing to work out whether they can have the ability to immigrate. So basically we'll be working out whether species are moving further north. As well as this, we'll be working out season length as well. So this is going to be based on a combination of plant and climate variables, and this will be really good to put into the analysis. But of course, there's some we don't have access to at the moment, and these are the ones that I've just faded out here. And as a result of that, it means that we lose these interactions, which is a shame, but there is only so much that we can model in the time that I have in a PhD. You know, I'd love to work on this for years, but there's only so much we can do. So I am hoping to continue looking at this in the future, but for my PhD, I'm going to be focusing on these interactions. So this leaves us with these variables to do the analysis on. So we have those related to the moths, those related to the plants, and the explanatory variables as well. And this is what the initial models will look like. So first I'm going to do an analysis on the moth species I have the data for, and see whether their phenology has changed, which climatic variables are associated with that change. And then I'm going to do a similar analysis for plants, but focusing more on whether the plant phenology has changed. And out of this, I'd hopefully get whether the magnitude and direction of phenological change changed, whether multivoltinism has changed, whether they're generalist, whether they're able to move, season length, host plant phenology, and whether they require a specialised habitat. And this is really important information to get out of the first models, because I want to get a really good look at how these moth species are responding to climate change. And the reason I really want to see how they're responding is because I have some really big questions I'd love to try and answer. So I would like to be able to use this analysis to work out what the risk of species losing synchrony is. So species are changing their phenology. Several studies have found this already, but what is the risk of multiple species losing synchrony with their food plants? So like the winter moth and the oak tree, the winter moth is now appearing not in sync with when the oak leaves are coming out, and this is impacting species. So how many species are undergoing this loss of synchrony, and how widespread is it going to be? And it would be fantastic if we could use the results of the model to work out where it's likely to happen and what these drivers are as well, so we can work out which species are going to be impacted this in what habitats and where. And I think this will be really important for future conservation targets, so we can work out where we need to focus on helping moth species continue to survive. So hopefully this mind map now makes a little more sense, and you've learned a little bit about the planning process that goes into ecological models on a large scale, like those involved in a PhD analysis. I'd love to answer questions, so please feel free to get in touch. And I'd just like to say thanks to my supervisors, Professor Stephen Rushton, Dr. Gavin Stewart, and Zara Patterson. Thank you very much.